Okay, so when we're looking at our organic chemistry reactions, some of the things that you need to know are the mechanisms behind those reactions. So I'm just going to go through a few of them. The first thing we need to know is that there's two different types of mechanisms. The first one we're going to look at is homolytic fission. So homolytic fission, if I take a compound and I split it, when I break that bond between those two atoms, each atom is going to take one of the electrons. And we represent that by a solid dot, just like that. So each one has one of the electrons, so it's split evenly. And those with the solid dot we call free radicals because they are very, very reactive. So our one type of mechanism that we have using homolytic fission is free radical substitution. So free radical substitution means I'm going to substitute one thing for another by attacking it with a free radical. And that takes place in three different steps. There's the initiation step, the propagation steps, and then the termination steps. So the initiation step, the very first one that we need to go through, that is if I have any halogen, I'm just going to use Cl2 for example, and it comes into contact with UV light. UV light gives it enough energy in order to break the bonds to react. So it has to be under UV light. If there's no UV light, it's not going to react because it doesn't have enough energy. And when that UV light is applied, it's going to take the bond between the two chlorine atoms and split them so that each one takes one of the electrons. So I have two free radicals. So this is the initiation step. Now that I have the free radical, then I can move to the propagation steps. So the first one is this free radical is going to attack my other alkane that I have. This could be any alkane, so it could be CH3, etc., depending on how many carbons there are. This is just going to be a one carbon compound, plus my free radical, which is then going to take the hydrogen from my alkane for itself to become a solid molecule, and that's going to leave the alkane without one of those atoms. So the alkane is then going to become my free radical. Now that free radical wants to become whole, so it is going to attack the next thing, which is going to be a chlorine molecule. So when this attacks the chlorine molecule, it takes one of the chlorines and it leaves the other one as a free radical. So that now free radical can then go and attack the next thing, and this can happen in a cycle until there is a termination step. And in a termination step, the free radicals join each other. So either that free radical can join with that free radical. So I can have my CH3 free radical plus my Cl free radical to form CH3Cl. Or that free radical can join with itself. So I can have the CH3 plus the CH3 together to make C2H6, and I go from methane to ethane. So those are all the different steps for the free radical substitution, where I take an alkane and I turn it into a halogen alkane. So if we look at the different type of mechanism, the second one that we have is called heterolytic fission. So heterolytic fission, when I split a molecule and they become two separate atoms, what happens is the more electronegative one takes both electrons from the bond. So when we're splitting it up, what happens is where the bond is, we will draw an arrow towards the atom that is taking both electrons. So in this case, between H and Cl, Cl is more electronegative, so it will take both electrons. And that will leave us with hydrogen without the electrons, so it will form a positive ion, and chlorine becomes negative because it took both electrons. So what that means is the hydrogen is now positive and it's lacking electrons, so it becomes what we call an electrophile because it is an acceptor of electrons. Because it's positive, so it needs the electrons to be whole. And the negative ion becomes a nucleophile, which means it is a donator of electrons because it has extra ones to give. So when we create electrophiles and nucleophiles, then our mechanisms follow depending on which ion we create. So we have electrophilic addition. I am going to add something. So I have an alkene with a halogen will make a halogen alkane. So I'm adding because the alkene has a double bond. So I'm going to break the double bond and I'm going to add the halogen to it, and it follows electrophilic. So if I look at my mechanism, I have an alkene with a double bond. As soon as a halogen comes close to the double bond, there's a whole lot of electrons there in that double bond. So negative electrons repel each other. So as this comes close, the electrons that are sitting in this bond in the bromine get pushed from one to the next. And what that causes is this bromine becomes positive and this bromine becomes negative because it's pushing all the electrons downwards away from where our double bond is. So now this positive bromine can take electrons from that double bond, and this negative bromine can take electrons from the bond between the bromines. So we represent that with arrows in the direction that the electrons go. So they go from this double bond to this bromine, and from this bromine bond to that one that we wrote negative. So when we're filling in our mechanisms, we need to show that our bromine gets a positive charge when it's close to the double bond, and the other one gets a negative charge. And our arrow goes from the double bond to the bromine, and from the bromine bond to the one that's furthest away. And that is then going to form an intermediate where we have our carbons single bonded now because we broke that bond. And when we broke that bond, we joined it to the bromine over there. And our hydrogens all stayed the same around there. But now we're missing one extra bond because we broke this one and we took the bromine. But now this becomes a positive ion because it is missing a bond. So now this bromine over here that took both electrons is still sitting free, but it took both the electrons, so it has a negative charge, and it has the electrons to now give to this positive carbon. So we draw an arrow from where the electrons are to where they can go. So from there to there. And that will end up with our final product where we broke our double bond and we added bromine to each side. So that's the mechanism for electrophilic addition. The other heterolytic fission mechanisms we have is we can have nucleophilic substitution. So now substitution means I'm swapping one thing for another, and it follows our nucleophilic mechanism. So our examples of that is we will have halogen alkanes either with sodium hydroxide in solution or with our hydrogen cyanide in ethanol. If we use the hydroxide, we're going to make an alcohol, and if we use the cyanide, we are going to make a nitrile. Either way, the mechanism will be the same though. It's still nucleophilic substitution for either that or that. So our important ion in there is either the OH or the CN. That's going to follow the mechanism. Now, because we're dealing with halogen alkanes, they could be primary, secondary, or tertiary, meaning if it's primary, where the halogen is, that carbon that it's attached to is attached to only one other carbon group and hydrogens. If it's secondary, the halogen carbon will be bonded to 2 other carbons, and then tertiary is 3 other carbons. So they have different mechanisms depending on whether it's primary, secondary, or tertiary. And the only ones we need to know are the primary and the tertiary. So, starting with the primary, that primary halogen alkane nucleophilic substitution we call the SN2. S for substitution, N for nucleophilic, and 2 represents the rate of reaction. So this is the SN2 mechanism. And what is going to happen is I'm going to have my halogen alkane, and coming along, I'm going to pick OH, but it could also be CN, and it has taken both electrons when it broke away, and it has a negative charge. So in this bond here between the carbon and the bromine, bromine is very electronegative, making this bond polar. So, because it's a polar bond, it means that the carbon becomes positively charged and the bromine becomes negatively charged. So we add a positive charge by the carbon and a negative charge by the bromine. And then what's going to happen is this OH with its extra electrons is going to give them to the positive carbon. So we're going to draw an arrow from our electrons to our carbon, because that's where it's going to give them to, because it has lots of electrons that are negative and the carbon is positive. And the bromine is going to take the electrons away from the carbon. So we're going to go from that bond to the bromine, because the bromine is electronegative, so it's going to take all the electrons. That forms an intermediate compound where we are going to be making an OH bond. At the same time, we are breaking the bromine bond. So we represent those by dotted lines attached to that. And you know that carbon can't have 5 bonds in the end. So that means one is getting made while one is getting broken, to end up with just the OH attached to make our alcohol, plus the bromine that came off. That has a negative charge because it took the electrons. So that's the primary halogen alkane mechanism. So then if we look at the tertiary halogen alkane mechanism, now, see, it's tertiary because the bromine carbon is attached to 3 other carbons. And what you're going to look at now, first thing that we're going to do here, same as over there, because it's carbon with bromine, carbon is going to get positive charge and bromine is going to be negative because it's a polar bond. So we're going to fill in our charges of positive and negative. Okay, and don't forget that's delta that we draw. And we are going to show that bromine takes the electrons from the bond between the carbon and the bromine. So we draw an arrow from there to the bromine. And that means that bromine comes off as a negative ion. And in our intermediate, it leaves carbon with a positive charge, because now it's come off, so it's missing a bond. It's still got the 3 C's around it, and it's just missing that one bond. And that means that the OH that has the electrons is going to come in, and it is going to give its electrons to our carbon. So we're there, they both happen at the same time. Now for the tertiary one, first step is the bond breaks, and then the bond gets made in the second step. And that ends up with our final compound, with our OH group, and the bromine that was left with a negative charge. So you end up with the same thing, except that there it goes in one step, and there your arrows are in 2 separate steps. And then the other mechanism that we have, the very last one that we need to look at, is our nucleophilic addition. So nucleophilic addition, now I'm adding something. So usually I'm going to break a bond and I'm going to add it, but now it's nucleophilic instead of electrophilic. So the first one with the alkene was electrophilic addition. Now nucleophilic addition is with a carbonyl. So when we talk about carbonyl, it means aldehyde or ketone. Both have a C double bonded O. And this is the carbonyl that is going to be reacting. So we take that carbonyl group, and if we react it with hydrogen cyanide, the cyanide is going to be added to where our double bond was when we were going to break one of those bonds, as well as the H is going to be attached to the O. So we make a hydroxy where the OH is and a nitrile group at the end. So if we look at that mechanism, there I've got my carbonyl. So this, it could be a C and a C on that end, meaning it's a ketone, or it could be C and H, meaning it's an aldehyde. Either way, the mechanism is going to be the same. So I am going to have a cyanide ion that has already been split from its hydrogen, and it took both the electrons, making it negative. The carbon and oxygen is super electronegative. So this polar bond means that the carbon is going to get a positive charge and the oxygen is going to get a negative charge. So what's going to happen is between our positive and our negative one is going to take the electrons from the bond. So we're going to draw an arrow from our double bond to our oxygen, because the oxygen is going to take the electrons. And then because our carbon is left positive, the cyanide is going to give the electrons to that positive carbon. So we're going to draw an arrow from the cyanide to the carbon. That means that this bond broke and it left oxygen there with just one bond. And the cyanide bonded to that carbon when that bond broke. So we ended up with our cyanide attached. And then those two bonds are our bonds left there. So whatever we have there will be there. Now, oxygen broke that bond and it took both electrons, which are attached to it. So it is left with a negative charge. That means that this negative charge can take another electron, and it wants to take the hydrogen from the cyanide. So we draw an arrow from there to the hydrogen, and between the H and the CN is more electronegative, so it takes the electrons from the bond between it. So the oxygen takes the hydrogen and it breaks off from the cyanide. So that means at the end, the cyanide attached, and it's still there, and the oxygen joined with the hydrogen. And we had our cyanide ion that's left that can go back and start again. Remember, those two bonds come from whatever is left in the compound, if it's an aldehyde or a ketone. But there we have our hydroxy nitrile. Okay, and then those are the only mechanisms that we need to know for our organic chemistry reactions.